Okay, maybe we can start. Are there any questions from last time? Okay, so last time we started discussing the question of infinities a little bit, and I was trying to tell you what our modern physical understanding of these infinities is. Okay? So when quantum field theory was originally developed, these infinities were mysterious things. It wasn't quite understood what they were. But now, the way we understand them is that we realize that, to define the quantum field theory, you should really try and define the you should think of this quantum field theory as coming from some more fundamental theory, which is defined at some microscopic scale. And, the parameters that we see at low energies in low energy experiments are not the same as the parameters that go into the definition of the theory. Rather, there's some combination of those parameters. And the physical example I was giving was, if you hit this table, you'll get some waves. You can write down some effective field theory of the waves. But, the intermolecular attractions of the different molecules in the wood here are not, things that are directly relevant. Rather, you want to describe this effective field theory in terms of some low energy parameters. What's the velocity of the wave? How fast does it dissipate, and things like that, right? And so one has to ask how those parameters are correctly related to the microscopic parameters. And when one does that, the infinities go away. So the basic principle in infinities is you should relate one set of low energy experiments to another set of low energy experiments. In this case, for instance, you might directly measure the velocity of the waves by means of one physical experiment, and then you could use that into another physical experiment, right? You could ask, or maybe you're looking at light as it goes through water. So you could ask how that velocity varies with frequency, and what you do is you directly measure the velocity at one frequency, and then you could try and say, what happens if I change the frequency, rather than trying to compute everything in terms of something, in terms of some interaction between the different atoms and so on. And if you did that, if you did try to work in terms of these bare parameters or these parameters of the microscopic theory, it's not surprising that you would expect to get all sorts of divergences, or all these bare parameters, all sorts of large numbers appearing, because in the end the kinds of scales at which you're probing the system are very different from the kinds of scales at which this theory is, this microscopic theory is being defined. Now you might also wonder, why it is that this thing doesn't occur, in other systems. Why don't you encounter this when you study other systems? And in some sense, the reason is that when you write down quantum field theory, you're really trying to write down some microscopic theory that describes everything, right? Describes the whole world. You're not saying here's one particle, and you're not trying to write down the theory of just that particle. Rather, you're trying to write down some microscopic physics which gives you effectively the theory of that one particle. So quantum field theory is kind of designed this way, right? Where you try to guess some microscopic physics, you try and postulate more degrees of freedoms than the one you can directly observe, and then you try and extract some low energy physics in that. And this is kind of the reason you don't see these phenomena occurring in other situations in classical physics and so on, and why it was new to quantum field theory. But anyway, this is our modern understanding. But there's one more thing you should realize, which is just something about how it is that interactions grow and decay with energy. So I said that it could be that there are some parameters in the microscopic theory, and what you see at low energies is just some set of low energy effective parameters. In fact, just some basic dimensional analysis in our field theory will help us figure out what these effective low energy parameters should be. Okay? So let me just explain that to you. This was something in your assignment. Remember, we've been working in units where h bar is equal to c equal to 1, and therefore there's only one dimensionless scale, which is L is equal to m inverse. Okay. In these units, we also have, we can ask what are we can ask what are the dimensions of various couplings. Okay. So for instance, when you take the action, you write down half of d mu phi squared, and this is d4x. Okay. And this should be dimensionless. It shouldn't have any dimensions, right? Now this here is a 1 over L squared. Right? This here is an L to the 4th. Right? Therefore, this phi squared should also have the dimensions of 1 over L squared, so that this whole thing is dimensionless. And therefore, you would conclude that phi has the dimensions of mass or L inverse. Okay. Using this, you can figure out what the other dimensions of various other couplings are. For instance, what is the dimension of, we've been studying two theories. So what's the before that? Right? There's m squared phi squared. This is one term. And this guy obviously has the dimension of mass, right? I mean, this is the mass, so it's not surprising that this has the dimension of mass. And you see this is correct because the action looks like m squared phi squared d4x. The action has to be dimensionless. So you have phi square, which is mass square, therefore this should also be mass square. Then you can ask about other theories. For instance, so what is the dimension of this G? This is this model that we've been studying, right? Which has two complex scalars and one phi. Mass, right? So this also has a dimension of mass because this is a complex scalar, right? And this is another real scalar. Therefore, this has the dimension of mass. Okay. When you really study the Yukawa coupling, it might be different. Okay. So right now these are just complex scalars. This dimension Z, this naively doesn't have any dimensions at all. Okay. Now, why is all of this important? All of this is important because you can start asking, what is the effect of different couplings at different energy scales, right? You see, when you ask this kind of a question, how do you answer this question, right? You could say, well, is the mass a large mass or a small mass? In fact, the point is that this is a meaningless question because, as you know, in physics, if you want to ask the question of whether something is large or small, you always have to ask the question in terms of dimension-less quantities, right? You can't say, 1 centimeter is a large scale or a small scale. Sometimes we say, 1 micrometer is very small, but that doesn't actually mean anything, right? 1 micrometer might be huge for if you look at atomic scales or the size of the proton. What we mean when we say 1 micrometer is small, actually is that compared to human scales or compared to the size of a human being, it's small, right? So we're always talking about dimension-less quantities. So in this case, you have to, so given any such coupling, you have to form a dimension-less quantity. Okay. In the case of the mass, what is the coupling that you can form? Well, it's obviously if the energy scale is lambda, the dimension-less coupling is m over lambda. Okay. Now, how does this behave at high energies and at low energies? Okay. Become small at high energies. You see, because at high energy, lambda becomes large, right? And you see why we have to form dimension-less parameters, right? So if you're doing an experiment and the experiment is being performed at some energy lambda, then how can the mass enter the answer for whatever experiment you're doing it at? It can only enter through this, can't enter through anything else, right? And therefore, you see that this coupling constant for the mass becomes small at high energy and it becomes large at low energy. This kind of coupling is called a relevant parameter. Okay. Okay. What about this guy, G? Same thing, right? the coupling that you form be G by lambda, same properties, right? Also a relevant parameter. Okay, what about lambda? Naively, because it's already dimensionless. Okay, so this kind of coupling, which doesn't have any dimensions, is called a marginal coupling. Okay. Okay. Now it turns out that when you add quantum effects, and this is a prediction of quantum field theory, it will turn out that this property of lambda will change. Okay. So this coupling can become marginally relevant, or it can become marginally irrelevant. Okay. It might happen that this coupling develops a property as a result of quantum fluctuations that it becomes more important at high energies and less important at low energies. Okay. In which case, it becomes more. What did I say? Okay, it could. I forgot what I said. It could be that it becomes small at high energies and becomes large at low energies. In which case, it would become a marginally relevant parameter. Or it could be that it becomes large at high energies and becomes small at low energies. Okay, in which case it would be a marginally irrelevant parameter. In the case of the lambda phi 4 theory, we'll find that this coupling actually has a property of being marginally irrelevant. So it becomes large at high energies. And in fact, so this is, we'll compute this property later. But naively, just from dimensional analysis, you can't tell, which way things are flowing. You have to compute some quantum corrections, which we'll do to see what's happening. Okay. Okay. What's an example of some other coupling which has the opposite property? Can you think of some other coupling that has the opposite property? Well, for instance, let's say I was to write down G6 phi 6 term. Okay. What would be the dimension of G6? What should it? Yeah, so it would be 1 over n squared, right? Okay, so this is the kind of coupling that has the property that if you make dimensionless parameters, then the dimensionless parameter looks like G6 times lambda squared. Okay, this becomes large at high energies. Becomes small at low energies. This kind of coupling is called an irrelevant coupling. It's called irrelevant, where do these terms come from? It's just a question of what the low energy behavior is. Okay? So this kind of coupling becomes irrelevant at low energies, doesn't have any effect at low energies, you see? That's why it's called irrelevant. That kind of coupling is relevant, very relevant at low energies. Okay? So this kind of coupling is called irrelevant. Okay, this is the phi 6 theory. Have you guys heard of some other coupling constant in nature which has the property of being irrelevant? QCD. No. The Yang-Mills coupling is marginal, and in fact, it has the property of being marginally relevant. So that was the famous thing about finding the QCD beta function. You see, QCD becomes asymptotically free. What that means is, if you go to very high energies, then at very high energies, it becomes small. Okay, so it behaves like this. Coupling becomes small. On the other hand, if you try to take quarks and pull them apart, then they become strongly coupled. But nevertheless, the classical coupling constant of Yang-Mills theory is marginal in the sense. Okay. This effect that we're talking about is a quantum effect. No, can you think of some other coupling in nature which has the property of being irrelevant? Nobody? Really, no guesses? You don't know any coupling that has the property of being irrelevant? Yeah, exactly. Gravity, right? Gravity is an important coupling which has the property of being irrelevant. Why is it irrelevant? Because how does the coupling constant go? It's G Newton, right? So how, what is G, if you look at what the how does G Newton go? If you look at what the dimensionless coupling constant is, you'll find that G Newton has the property of being 1 by m Planck squared. Okay? And the coupling constant, in fact, therefore looks like G Newton times E squared. This is actually expected. Remember, gravity is coupling to energy, right? So if there is more energy, then gravity couples more strongly. Something which has more energy gravitates more strongly. So dimensionless coupling constant looks like G Newton times energy squared. So you can write down, some effective coupling that looks on kappa. I usually write in terms of kappa, which is square root of G Newton. Doesn't matter. The point is the dimensionless coupling is this, right? And this has the property that it becomes large at high energies and becomes small at low energies. So this is an example in nature of an irrelevant coupling. Gravity is a famous example of an irrelevant coupling. Okay. Apart from gravity, by the way, there's a very good reason. So, it'll turn out as we do this that theories which have marginal and relevant parameters, okay, have the property of being renormalizable. And theories which have irrelevant parameters are what used to be called non-renormalizable theories. Okay, so actually, sometimes theories with relevant parameters used to be called super renormalizable, but this terminology people don't use nowadays so much. Okay, they use theories with marginal so these are renormalizable theories, and then there are theories with irrelevant parameters, and these were what used to be called non-renormalizable theories. Okay. Now, physically, we haven't done any calculations yet. Why is it that this happens? The reason this happens is that coupling constants which become large at high energies, okay, whose effect grows at high energies, are sensitive to the UV physics, are sensitive to what is happening at high energies. Okay, so coupling constants which become important at high energies are sensitive. You can't guess what's happening at if you make some low energy experiments and then you want to ask how does the theory behave at high energies. Well, it turns out because the effect of this coupling becomes important at high energies, there are quantum fluctuations, and you cannot completely predict from low energy physics what's going to happen at high energies. On the other hand, if you want to ask just what happens at low energies, then these couplings just become completely unimportant at low energies. Okay? Whereas those couplings, have the property, have a different kind of property. Right? They have the property that as you go to high and high energies, those couplings becomes less and less important. Therefore, for those kinds of theories where you have relevant couplings, or perhaps where you have marginal couplings or marginally relevant couplings, it makes sense that you can define some UV completion of the theory. You can make some guess for the UV physics, okay, which might not be the way the physical world works, but there's a way to mathematically complete the theory all the way into the ultraviolet, all the way to very high energies, so that it reproduces the results of low energy experiments. Okay, and that's basically what renormalizability does. Right? You make some guess for what happens at high energies, which may or may not be the way physically things work. However, it doesn't matter if you're asking only low energy questions, because in the end, that the UV physics is not going to be important. Okay? Whereas in this case, when you look at these kinds of couplings, so these kinds of couplings, first of all, are not important at low energies in leading order experiments. But if you insist on knowing, what their effect is, then you have to make some guess for the UV physics, and it's important what guess you make. Right? So really, the statement is that these theories which have irrelevant couplings are sensitive to the UV physics, whereas those theories are not so sensitive to the UV physics. Okay? So this is really a question of yeah. It depends. If you have couplings which are becoming strong at low energies, then you might, perturbation theory might break down at low energies as well. QCD is an example of the kind that you said, where at low energies, you can't work in terms of the quarks because the theory becomes strongly coupled. Yeah. Theories which are irrelevant. Huh? Irrelevant is non-renormalization. Yes. So what? So it becomes irrelevant at high energies. Well, irrelevant is just a name for a coupling that becomes strong at high energies and becomes, less strong at low energies, like gravity. And that's the name is just so the name for that is irrelevant. Irrelevant means it becomes irrelevant at low energies. Okay. Non-renormalizable means that you can't define some UV completion of the theory, precisely because the coupling is growing strong at high energies. So there's no way to just make some guess for the UV physics, which just works all the way to arbitrarily high energy scales, and that's because this coupling is growing strong at high energies. It's not a question of perturbation theory. It's not like non-perturbatively we know how to make a guess for the UV physics that will allow. One way to think of it is, what happens if you define the theory on a lattice? Okay? So the question is, if you define the theory on a lattice, in this case, you make some guess for what some parameters in the lattice are, and you adjust those parameters in the lattice so that at low energies you get the right mass and so on. Okay. On the other hand, in this case, in the case of gravity, and then you can try and take a limit where the lattice scale goes off to 0, or the lattice energy goes off to infinity, and your theory remains well defined. In this case, however, what will happen as you try and take the lattice scale to 0 is that your theory will become more and more strongly coupled in the UV, and therefore you won't be able to find a UV completion. Yeah. Okay, so this is just some philosophy. We'll now do some actual calculations. Are there any questions about this philosophy? Or? Okay. Okay, so now I having said this, I want to come back to the practical problem of actually doing calculations, and in particular, understanding this issue of how quantum effects change the behavior of these couplings, and actually doing one loop calculations. Okay, so that's what we now want to discuss. Okay, so operationally, what perspective does this interest operationally? So what does this philosophy tell us to do operationally? Well, it tells us that the Lagrangian and we should okay, so the operationally, what this philosophy is telling us is that this Lagrangian we've been writing down, it's some bare Lagrangian. It's fine, it's some bare Lagrangian, but in the end, we should adjust its parameters. We should adjust its parameters in such a way that we get the correct low energy physics. Okay. Okay. Good. So let's look at this Lagrangian that we've been writing down so far for the phi-4 theory, right? So operationally, the statement is that this here you wrote down some parameters, right? These parameters were m and lambda and so on, but these parameters were really not the physical parameters that you necessarily measure at low energies. Therefore, you should write down what's called a counter term Lagrangian. Okay, which might have different parameters, so that the physical parameters you measure at low energies are these parameters m and lambda. Okay, what is this LCT? A phi okay, I'll try and stick to these numbers A, B, C, D, but I might sometimes get confused about which one we called A, which one we called B, and so on. Okay. Now, how do you fix these A, B, C, D terms? Okay, these just look like they're random. Well, you fix them by saying for instance, right, one data that you might provide is, you might say that in the vacuum, sometimes I'll write, actually, so, I'll write 0 because I kind of don't like writing omega, but when I write 0 from now on, this is always the full physical vacuum. Okay, we are never referring to the perturbative vacuum. Okay, so this is, that's because from now on in this course, we are never going to see this vacuum of the free at 0. It appears in perturbation theory, we know how to deal with it then. But whenever we write down some full Green's functions and so on, whether I write omega or 0, it's the same thing. So we could write down 0. What is this? This is the statement that in the vacuum, phi of x has no expectation value. Okay. Then we could have the statement then we could have the statement that I'll show you, and we'll parse the statement a little bit more. This is some statement about how the field has to be normalized. Okay? It'll do something to fix what this B is. Then we could have the statement that phi of x we'll say in a minute what this means, but phi of x corresponds to a field of mass m. This will fix A for us roughly, this will fix B for us, this will fix C for us. And we can say something about low energy 4-point scattering has some strength. This will fix for us this term D. Okay, these arrows are kind of indicative. If you start working to higher and higher order in perturbation theory, you will find that these counter terms in fact depend on all these different renormalization conditions that you put. However, physically you can see, this is kind of telling us that you need to shift off a constant from phi, and that's kind of what this is doing, right? If you shift phi by a constant, then you see it's like adding a linear term. So what is this saying? This is saying, this renormalization condition is telling us that whatever phi you have at low energies, you want to define the field so that it doesn't have an expectation value. There's nothing that says you have to use this convention. In principle, you could say, well, I want to define the field with some other expectation value, but that's just an inconvenient convention to use, right? So it makes sense to define a field that's 0 in the vacuum. Okay? So this renormalization condition you see intuitively will fix A. Okay? Then we want there's a question of how you normalize phi. Right? Let's say somebody uses the field phi and somebody else uses the field 2 phi. Right? There's nothing wrong in using 2 phi or phi. Right? How do you fix that normalization? Well, you fix the normalization in this way. And this and one way you fix the normalization in the Lagrangian is by saying that the coefficient of this term here should be half. Okay? So you see, changing this from half to half plus b by 2 changes what the normalization of the field is. That's why this will help us fix this b. Okay? Similarly, this c is like shifting what the mass is. You see, it's like adding to m squared. and therefore demanding that the low energy, that the mass of the particles that you observe is m, will help us fix C. And finally, this d is changing this coupling constant lambda, and therefore you see that demanding some strength of low energy scattering will help you fix this d. Okay. Okay. Good. Now similarly in the phi, in this other model that we had, which was this phi. Maybe I'll go to the other board. Where did I put it? There's this other model that we've been studying, which is this model which is this model 3. There the Lagrangian we are writing down look like d mu psi squared plus half squared. Let me try and get my A's and B's. That's LCT. Squared. Why did I call it G? Okay, so these I've given these things some names in my notes. I don't know if I'll stick to them. Okay. That's E psi squared. Psi squared. Okay. Okay. Once again we can add some counter term Lagrangian, right? And this counter term Lagrangian, has all these parameters. In this case, there are more parameters, right? There's a parameter that can go in front of. There's a parameter that can go in front of phi. There's some other parameter that can go in front of d mu phi squared. Some parameters can go in front of phi squared. Something which can go in front of d mu psi squared, e psi squared, and so on. Okay. Okay. Why is there no term linear in psi? Good. Why didn't we write a term linear in psi? Yeah. So what's the reason we didn't write a term linear in psi? Yeah. What's the reason? Good. So can you say it a little more precisely? Yeah. You see, the point is that this theory has an SO2 symmetry. There is no term you can write down that's linear in psi, okay, which has an SO2 symmetry. If I write down psi, it will just break the SO2 symmetry. Okay. So symmetries sometimes will prevent the existence of some kinds of counterterms. Okay. So symmetries are a useful thing that tell us about what kind of counterterms are allowed. And conversely, we don't have to demand that the vacuum expectation of psi is 0, because the vacuum expectation of value of psi has to be 0. Okay. Okay. Once again, what should we demand? Well, we should demand This is the one particle state of psi, the one particle state of phi. These are different one particle states. This last thing, the way I wrote it, for some specified momenta. Okay, we haven't specified yet either for lambda or for g how these momenta are to be specified. We'll do that later. Yeah. Okay, so these are the renormalization conditions that we should put for this theory. And once again, you see that this will kind of fix for you A, this will fix for you B, this will fix for you C, this will fix for you E, this will fix for you D. Do you see how this is working? This is E, D, F. Yeah. Which signs? Yeah, well, they're just A, B, C, D, so it doesn't matter. Well, how does it matter what you call it? Yeah. Okay, good. So now let's start working out what some of these renormalization conditions do, and I want to tell you at least how the 2-point function behaves. Okay, so yeah, so for now I just want to make some of this a little more formal, just make it a little more precise, and then we'll start working out what these counterterms are. Yeah. Okay, let's first look at, we can do either theory. For now, let's just work with the phi-4 theory, but this theory also has some advantages. It has some more counterterms you can show, or some different kind structure of one loop diagrams. The phi-4 theory also has some advantages, so we'll kind of work with both. Yeah. Okay, so let's first look at this counterterm. Let's look at that counterterm, which said 0, phi 0 equal to 0. You can look at that counterterm in both settings, both for the phi-4 theory or for the G phi dagger phi theory. What is the vertex that corresponds to this A phi? What vertex would you write down? Yeah, it's a linear vertex. It just has one thing sitting out of it, and you add for this A, right? So what does this renormalization condition tell you? That 0, phi 0 is 0. It tells you that this plus all other graphs with one line of this kind, right, is equal to 0, right? That's what this renormalization condition is telling us in terms of Feynman diagrams. Okay, but that's nice, because what does this tell us? It tells us we never have to work out what A is. All A does is it sets all these graphs to 0. Therefore, you never have to work out what such a graph is either. If someone said, in this G phi dagger phi theory, this is, or maybe in the phi 4 theory, let's say, but okay, in G phi dagger phi theory, it's kind of simpler. Somebody said, look, what's the value of this diagram? You never have to work out what the value of this diagram is, because the value of this diagram is always going to be set to 0 by that counter term. Yeah. Okay. So, sometimes these diagrams are called tadpoles. Are not irrelevant, is not whatever, can be neglected. Okay. Okay. Okay, good. Hey guys, it's getting a little stuffy here. Can we switch on this AC, please? This one? This one not working? No, this was off. This is off, I think. Thanks. Yeah. Sorry, what? This is a connected diagram. Yeah, it's connected. It's not disconnected. Nothing's going to anything else. That's right. So you could have a diagram of this kind, which is, let's see. In all theories, this is a connected diagram. Why is this not connected? No. Connected and disconnected just have to do with the two parts of the diagram. There are no two parts of the diagram. There's only one part. This is a connected diagram. I mean, connected doesn't mean this is not a bubble. A bubble is a diagram which has no external legs. This is not a bubble. This has one external leg. And you never have to worry about that either, because of the renormalization condition. Yeah. Okay, good. Let's now consider the other two conditions that we have, about this one. This q phi x is equal to b 0, the things that set b, and the things that set this c. Okay? So I want to reframe these conditions in terms of the 2-point function, and the results we are going to have right now are going to be some important formal results, okay? Which will be important later as well. Okay, so I'm not going to right now calculate these terms for you, but I'm going to I'm going to reformulate them in terms of slightly different quantities. Okay? So do you see that I'm talking about the condition which is one, the normalization, which sets the coefficient of the d mu phi squared, and the condition about the mass. Yeah? Okay, so about the normalization and mass. In terms of this guy, which is the Green's function. There's a propagator. Okay. It's the usual time ordered propagator, which is the only kind of propagator we'll see in this course. Yeah? Okay, so let me first say some things about this propagator. I'm going to prove two results about this propagator. One of them is called the Chelin-Lehmann spectral representation theorem. And then I'm going to introduce another concept which is called the self-energy. And in terms of those things, we'll have something to say about what these renormalization conditions are. Yeah. Okay, good. So So I'm going to say two things. One of them, it's called Kellen-Lehman, but actually it's spelled as Kallen. Okay, so Kellen-Lehman, but doesn't matter. Yeah. So if you want to calculate that, so what does it look like? Well, it looks like, let's call this G. And let's insert a complete set of states here. Okay, so it looks like phi of x times some energy eigenstates. Plus, you know, theta of y0 minus x0 times something similar, which I won't write. Okay, it'll just kind of it'll just come by analogy. Okay, so you see, we have phi of x. It's always later on the left. So consider the case when x0 is larger than y0. This is a complete set of energy eigenstates. Okay, it includes in particular the vacuum, but the vacuum doesn't give us any contribution from what we said above. Okay, so the first contribution from here comes from single particle states. So let's call these guys K. This is a sum, but in fact we know how to do the sum. We know what the measure and so on should be, right? This is just single particle states. We know what the measure should be, right? Plus what is this answer? If I use this renormalization condition and I tell you, I know what this is, right? This is just supposed to be e to the I k dot y, e to the minus I k dot x, right? And similarly for the other time. So what is this sum over single particle states going to give you? Yeah, it's going to give you the usual free field propagator that we've already studied, right? You see, we know that this looks like e to the minus I k dot x. Okay? This looks like e to the I k dot y by our conditions. There's a theta of x0 minus y0. On the other side, there's another term which has a theta of y0 minus x0. This is what we've already been studying in free field theory, right? We studied this a lot in free field theory. So this sum of single particle states just gives you and it doesn't matter. Okay, this is just the sum of single particle states. Is it clear what I'm doing? Sorry. You see, I took this full propagator. Then I said you can insert a complete set of energy eigenstates. The vacuum doesn't contribute. The next term that contributes is the sum of single particle states. The sum of single particle states sums up to give you the usual free field propagator that we have. Is this clear? Yeah. Okay. What about now the sum over multi-particle states? Right. So let's do that. There's another term. Okay, this is just term one. It's the sum over single particle states. Okay, but there are other terms. Those other terms look like n is not a single particle state. This is the second term. where this sum runs over all states which are not single part, which are two particle and higher states. In the free field theory, such states never occurred. You see, they never occurred because the field phi never had any overlap between the vacuum and two particle and higher particle states. In the interacting theory, the field phi has an overlap between the vacuum and all particle states. You can't just say, the field phi only creates single particle states. That's not true. So this term is not zero. However, we don't actually know what to do about this term because, we don't know what the measure over this is. I mean, some measure over multi-particle states. Maybe we can write that down formally, but we don't have any condition on what this spectral representation should be. Right? You see, the reason we were able to evaluate this was because we had a renormalization condition that told us that 0 times phi of x times 0 was e to the iqx. Right? Or sorry, q times phi of x times 0 was e to the iqx. That told us you could evaluate these matrix elements. They are fixed. But I can't fix the matrix element for all of these guys. If I did that, that would be specifying the field. And that's supposed to be specified by my dynamics. Okay? You see, specifying that matrix element is really only a question of specifying one number. It looks like we are specifying a whole function, but in fact, most of the function is just fixed by Lorentz invariance. So that condition I could also have written as that's really the condition I'm trying to fix. Even though I wrote it as q times phi of x times 0 is e to the iqx, it can equivalently be written as this condition. Once you have this condition, then you just do some transformation and you'll find that this will become e to the iq dot x. So it's really a question of really fixing the normalization of phi. You multiply phi, you can change this. Similarly, even here, you notice that this, I'm assuming that the 4 vector, the energy and the momentum that corresponds to this, I'm calling that qn. But I can pull out the dependence on x minus y. It always looks like qn dot y minus x. Okay? And what remains here is the mod squared of 0, 5, 0, n. That's also the mod square that remained there, except that I set to 1 for single particle states. Okay, is this clear? Okay, good. So now what can we say about this? It looks like this is some bad term, but in fact we can put it in some nice form, and that's done as follows. Okay. Look at the Fourier transform of this guy. Let's call this Z. Okay. 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 This Fourier transform, it looks like okay. I'm just defining the Fourier transform. So what we have here is some sum, right? We have some sum over e to the iqn dot y minus x times 0, 5, 0. I'm just defining the sum over this to be this. Okay. I'm writing this as a sum, but really I should write it as an integral. The integral here was just an integral over d4z. The sum here is a sum over n. I'm writing a sum here, but really I should write an integral. Okay. But the reason I'm not writing integral is if I wrote an integral, I'd have to make precise what the measure of multi-particle states and so on was. Okay, good. Now, what can I say about this guy? You see, what does it depend on? This thing. It only depends on P because everything else is getting summed over. This Qn is getting completely summed over, right? It's a sum over n. This Qn is just telling you what the energy and the momentum is. That relation could be very complicated for multi-particle states. Maybe it depends on the coupling constant, but it's getting summed over. So the only thing this can depend on is P. Okay, how can it depend on P? Can it depend just on P? You see, it can't depend just on P because this is something, whatever it is, it's Lorentz invariant. So it can only be a function of P squared. So we'll just define this to be sigma of P squared. It cannot be a function of anything else. we know a little bit more about what this is. We know that the sigma of p squared has no support for p squared smaller than or equal to m squared. Because whatever multi-particle states there are, right, they always have an energy which is larger than single particle states. So, this function never has any support when p squared is smaller than m squared. See, this p is the thing that's going here. So this function is some function, it characterizes the theory, but it doesn't have any support for p squared smaller than m squared. It's a function only of p squared, and importantly, it's positive. It's positive because you see here you're summing over a set of positive terms. You're summing over mod of phi of 0 n squared times something. So everything you're summing over here is positive. So whatever this function is, it's positive. It doesn't have any support below m squared. Could be 0, but can be nothing else. Okay. Okay, good. Now this is useful because this original expression that we had, right, we can write this as e to the I qn dot z okay. Okay, now in this integral that you have over p d4p, maybe I'll pull this down. Maybe I'll rewrite it. Just using the inverse Fourier transform, this expression that went in there, I'm getting confused about my two twice. 1 second. Sorry. I should write this e to the I p dot z equal p to the 4. I'm mistaken my notes, but yeah. Okay. Huh? No, there's no delta because the sum over delta went away. You see, that was by the, what? Sigma p square already there. There's no delta because the sum over delta went away. Okay. This was just the definition of the Fourier transform was sigma of p squared. Okay. So therefore, the inverse Fourier transform tells you that whatever this is just given by sigma of p squared times e to the I p dot z times d4. What theta term? Oh, the theta term is just sitting outside. I'm just looking at this term. Okay. There is a theta term, okay, but the theta term is just sitting outside of all of this. I'm just looking at the left part of this. Okay, good. Now, you see, this term I can write as, I can insert a 1 in this. So you can write this as sigma of p squared times a 2 pi p squared minus a squared times a d of a squared by 2 pi times a d4p by 2 pi to the 4 times e to the I p dot z. Okay. I didn't do anything here. I just said that, I put p squared minus a squared equal to, I introduced some parameter a squared. Then I integrated over a squared. Okay. If I do that, clearly that just absorbs this delta function. So instead, I've just inserted for fun an integral over a squared. However, you now see that I can switch the order of the integral, and I can write this as integral of sigma of p squared times e to the I p dot z times 2 pi times delta of p squared minus a squared times d4p by 2 pi to the 4th. And then I can integrate this whole thing with respect to a squared. Right? Okay. But, this answer is something that we've seen before. Right? This answer, is like saying that you put, this just sets p squared equal to a squared. Right? So this just pulls out sigma to be sigma of a squared. So I can pull it out here. Sigma of a squared times dA squared times this integral e to the I p z times 2 pi delta of p squared minus a squared. Okay. Okay. Now look at what will happen if you take the other term which also has the delta of y0 minus x0. Then you will get e to the I p dot z into theta of x0 minus y0 plus a similar term with a theta of y0 minus x0. Okay. You see, this term is just the usual term that appears in the propagator. Okay. If you do this integral, you will find that you just get p0 set to be the energy as if this was a particle of mass a, okay, and you get an integral of d3p. So this looks like integral of sigma of a squared times dA squared times integral of e to the I, p a dot z times d3p by 2 pi cubed times twice of square root of p squared plus a squared. Twice of p squared plus a squared. Did I use what? Yes. That's right. That's right. So I did that to do the integral of d4p0. So this just became an integral of d3p. This pa just means that I set the 0 component to be square root of p square plus a squared. Okay. You see, this looks a lot, if I now combine it with the term that has a theta of y0 minus x0, you see it looks a lot like a propagator of a particle but of mass a rather than a particle of mass m. So if you combine this result with the other result there, yeah, is a question? Yeah.
If I have already put sigma of p square at a square, then how come the delta function still remains?
How come what?
You have written sigma of a square, right, in the second line.
Yes.
So how come the delta function still remains? Because I think p square, you have put p square as a square, right?
Oh, that's true, but the delta function can still remain, right? If you have f of x, like saying if you have f of x, g of x, delta of x, you can write this as f of 0 times g of x, delta of x. You still have to, so I'm still using the delta function.
Oh, okay.
F of x and g of x are regular. I mean, this is a true statement, right?
Yeah.
Because I can set one of them just x equal to 0. I still need to do some integral of d of x, which I have there, but the delta function still remains.
Yeah.
Okay, good. So the net result is that so if you combine terms 1 and 2, the net result is actually very simple. It's simply that okay, and that's the answer that we're looking for. Yeah. Well, it's not a new mass. There's no, yeah. So this is sometimes written as e to the I p dot x minus y d4p by 2 pi to the fourth and sigma tilde of a where I've just written sigma tilde of a square as sigma of a square plus delta of m square minus a square. In this notation, sigma tilde of a squared looks like delta of a squared minus m squared plus sigma of a squared. So sigma of a squared has a delta function at a squared equal to m squared, and then it has some positive spectral density at higher things. Okay, it doesn't have other delta functions. This is some spectral density, it doesn't have other delta functions, but the delta function is the thing that controls a single particle mass. And then there's some continuum, which looks like you're summing over some continuous set of masses, but this is really just giving you information about the spectrum of the theory. Remember where the sigma came from? It came from the Fourier transform of that. So it was giving you some information about the spectrum of the theory, and that's where this is coming from. Okay, so this is called the Telin-Lemon spectral representation theorem. Okay, what do our renormalization conditions fix in terms of this 2-point function? They only fix this part of the 2-point function. They don't say anything about that. Okay, so our renormalization condition is basically just fixing this. Condition fixes the coefficient and location of the delta function. That is it. So another way of stating our renormalization condition is that when you think of the 2-point function, the 2-point function has a spectral representation. That spectral representation has a delta function. That delta function is at m square, where m square is the physical mass. Okay, and it has a coefficient of 1. Okay, so that's another way to say this. Okay. Conversely, if we think about the propagator in momentum space, this tells us the propagator in momentum space has a pole at p squared equal to m square with residue 1. Okay. Okay. I mean, 1 means, normalize correctly. It looks in terms of p squared. Yeah. What? What do you mean we had? We had just computed the free propagator. Where had we computed the propagator? We've never looked at the propagator in the interacting theory, right? We've just looked at the free propagator. So the renormalization condition is telling us in the full interacting theory, this is the condition we are putting on the propagator. So we didn't have, I mean, it doesn't mean anything to say we had this result. This is the result which, we had computed something in the free theory. In the free theory, of course, all of these things were met. Okay? We've never computed this full propagator or corrections to this propagator. And what this is telling us is even after we compute corrections, we should demand this.
So, but you have made a statement earlier. If field phi will satisfy those two, will satisfy that.
Is what?
Vacuum expectation is 0 and
Good. So our renormalization conditions are ensuring that the field phi we have can go into the LSZ formula. So our renormalization conditions are telling us that the field phi that we have has this property, and so it can be used in the LSZ formula. Okay, let me reformulate this in yet another way, so that it makes more sense in perturbation theory. So I want to reformulate this in yet another way. Okay. By the way, so I should have written G of P squared. Not G of P can't actually ever depend on P. It can only depend on P squared by Lorentz invariance. Okay. So what does G of P squared look like? Well, this is the term that we have. Right? This term, well, it looks like I by P squared minus M squared plus I. This meets the condition that we have. Whether you put the residue to be 1 or I depends on how you normalize things. Let's keep this normalization where you're keeping the I. Okay, good, because that's the one that comes in the Feynman rules. Yeah. Okay, good. But there might be other terms, right? G of P squared looks like this, but it might have other terms. For instance, let's say we're in the phi cubed, psi squared phi theory. Then, but this is a fermion line, you have a diagram of this kind. Okay. Or you might have other diagrams. Okay. In fact, these other terms have a simple structure. And the simple structure comes about as follows. Okay. We define the notion of a 1pi diagram. 1pi stands for one particle irreducible diagram. This is a diagram which cannot be cut by cutting one line. Is this a 1pi diagram? It is a 1pi diagram. It can't be cut into two pieces by cutting one line. What about this diagram? It's not 1pi, right? This is 1pi. This is not 1pi. Why is it not 1pi? Because I can cut it and break it into two parts. So we call the sum of all 1pi diagrams we define this to be minus I sigma of p squared. This is just our definition of sigma. Okay. This is just a definition of something that we call sigma. You just sum all 1pi diagrams. Whatever you get, you call that sigma of p squared. Okay. Maybe there are many 1pi diagrams. In general, this is the one loop term. There might be 2 loop diagrams, 3 loop diagrams. Just do all that sum and you call that sigma of p squared. Okay. So now what happens to the propagator? You see, the propagator looks like this. What are the Feynman diagrams? Plus 1pi plus, 1pi is just something we define. The Feynman rules don't tell us you're only supposed to sum over 1pi diagrams, right? The Feynman rules tell us you have to sum over everything. Okay, plus so on, right? So you see that the Feynman rules, you just get an infinite series of such terms. The nice thing is that this can actually be summed, because what's the sum of this? Let me sum it to the next page. Well, the first term we get looks like minus I by p squared minus m squared plus I epsilon, right? The next term that we get looks like minus I by p squared minus m squared plus I epsilon. Okay. Then we have this sum of all the 1pi graphs that we called plus I into sigma p squared. Okay. Then we have similarly, you keep going, plus minus I. So this term, gives you something that just looks like sigma p squared by this into sigma p squared so on, right? And it's just a geometric series, and the factor in every series just, that adds on every term is just sigma of p squared by p squared plus minus m squared plus I epsilon. So you can sum this geometric series. What does it look like? Okay, into, this is the leading term, and then you have 1 minus this is the first term, and then you have all of these other terms. Okay. Well, what does this do? You see, I can combine this denominator. I can write this as p square minus m square minus sigma of p square plus I epsilon. That's what the term you have here. And this term just cancels out. So the structure of the propagator is just this. And this guy, this thing that we are calling sigma, is called the self energy. Okay. 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 So this sigma, as you can see, is sensitive to what one loop diagrams are doing. These one loop diagrams, when you compute them, will have some infinities. This is telling you should set the counter terms so that this propagator has a pole at p square equal to m squared with residue which is 1 or I or whatever you want to call it. Yeah. Okay. What is the condition that puts in sigma? What is the condition that the propagator has a pole at p squared equal to m squared? What does that mean in terms of sigma? Exactly, right? So it just tells you that sigma of m squared is the same as saying that okay, that's one condition. What was the other renormalization condition that we had? That the residue should not change, right? What is that in terms of sigma? Is what? Yeah, you see, what does the residue do? Yeah, the residue. So sigma of m squared is we already said sigma of m squared is 0. Okay. However, imagine that imagine that sigma of p squared has some expansion. It looks like p squared minus m squared times sigma prime of m squared plus high order terms. We already know it has this form, right? Because we said sigma of m squared to 0, right? So it doesn't have any value at sigma of m squared. If you expand sigma of p squared around p squared equal to m squared, then it tells you that p squared times m squared times sigma prime. Sigma prime means the derivative with respect to p squared of this is equal to 0. But if this was non-zero, right, then this expression would still have a pole, but the residue would get shifted to 1 minus sigma prime of m squared. Right? And so you see that the statement that the residue of the pole is unchanged is the statement that residue of pole is unchanged implies that d by dp squared of sigma of p squared okay. So these are two of the renormalization conditions that we had, and you see you can fix them in terms of the behavior of the self energy at 0 and in terms of the behavior of the derivative of the self energy. You can also fix them in terms of the behavior of the spectral representation function, but in perturbation theory this is more useful. Okay, so far we've still just set some conditions and we've just rephrased the conditions. We haven't actually done any calculation. Next time we'll embark on actual calculations and I'll show you how these terms these renormalization conditions that we've now written in different ways can be used to fix the counter terms that we have and actually get physical results. Yeah. Okay, so this is all I want to say today. I will stop here unless there are questions. Huh? Is what C? Counter term C? No. The counter term is a number. Okay, the counter term never depends on p squared. Sigma is a function of p squared. The counter term is some number that you're going to put in the Lagrangian, but remember it's multiplying the Lagrangian. I forget what we called C actually. Anyway, it was something in 5 square, but that's going to be a number rather than m squared. Maybe you'll put that number to be 10 times cutoff squared or whatever, right? But it's not going to be a function. Sigma of p squared is a function of p squared. They're very different conceptually. So C is not p squared. Okay? The counter term is not sigma of p squared. Notice, by the way, sigma of p squared is a function, but we only set two numbers in the function. We set its value and we set its derivative. In general, sigma of p squared can do whatever it likes at other values of p squared. It's some function which has interesting behavior, but it's these two terms that set the renormalization conditions. Okay. Huh. Because you see, you want, so the sum of all diagrams, right? First of all, you can sum all 1pi diagrams, and then you can sum diagrams which can be cut into two parts, right? There are by definition only two kinds of diagrams. So if I already summed all my 1pi diagrams and I call those 1pi, then to make all diagrams, I just have to add them. I can only string them together. What else can I do? Which factors? Yeah, the factors did come. You see, there were factors, but the factors were very simple because the factors corresponded to propagators, right? So it's not that you just got the diagram. You got also those propagators that sit in the middle, but no other factors. There can be something, and that's a 1pi diagram. Yeah, that's a two loop 1pi diagram. Okay,
Sir?
good. So yeah, is there another question? Yeah.
Sir, apart from the fact that this sigma function comes from the diagrams, do they have any physical significance in the process that we are considering? I mean, supposing two scattering or something like that.
Sorry. Okay. What is that?
The question is,
I mean, yeah.
suppose
So
we
this is
are
kind of like the self energy name is kind of it's a name. Well, yeah. Yeah. I don't know what you mean by physical significance. This is the thing that enters the 2-point function. The 2-point function is an important, something important because it tells you, how things propagate at long distances. It's kind of, if you also tells you how the system responds to a source. So this is one important term. It's an important correction. It completely captures what the 2-point function is doing. Tells you the 2-point function in the interacting theory has this term, which doesn't look like p square, but has these additional terms. It's called the self energy because, it looks a little bit like, if you have just an electron which is propagating, that electron can itself, nucleate various virtual particles and then absorb them again. And if it absorbs them, you see, that's what the diagrams are doing, right? 1pi diagrams are you have one electron propagating, it emits some virtual particles and absorbs them again, and it keeps propagating, right? That's why it's called the self energy, because that electron is not interacting with something else, it's just kind of interacting with itself by emitting and absorbing some virtual particles. But beyond that, I don't know what to say. It's called the self energy because it doesn't involve interactions with any other particle, and mathematically it appears in the 2-point function.
okay, so then it will also have some contribution for calculating cross section, right? When you calculate the cross section.
What's the question? Sorry.
When we calculate the cross section, it will have some contribution like for the other diagram, right?
For sure, because it's in the propagator, right? So when you write a propagator, you actually should write this propagator with the sigma of p squared.
Yeah.
Is that clear? Or, yeah. Okay. Are there any other questions, or we'll stop here?